blood CSF barrier. Okay, barrier is formed because of that tight junction. Okay. So you see now the ependymal cells are essential in the production of CSF, as the choroid plexus may secrete up to 500 ml of CSF per day in the adult brain. Okay, so now it is saying that these are all ependymal cells. Okay, there is a secretion of substances along with water, and as I told you, this is known as CSF. Okay. And the secretion may be up to 500 ml per day in case of adult human being. Okay, the CSF is constantly produced, and in humans, the total volume is replaced about 4 times each day. Okay, so CSF it is produced, but it is also reabsorbed back. Okay, and in human, the total volume is replaced about 4 times each day. Okay, so every day it is said that it is replaced 4 times. Okay, within 1 day. Okay, now how CSF formation takes place? Okay, cerebrospinal fluid is formed at a rate of 500 milliliters each day in human. As I told you, 500 milliliters is secreted per day. This is 3 to 4 times as much as the total volume of fluid in the entire cerebrospinal fluid system. Okay, actually, the reason why this is 3 to 4 times as much as the total volume of fluid in the entire cerebrospinal, it means that 500 ml of CSF is secreted, but this 500 ml is around 3 to 4 times of CSF present at a time. Okay, all those in that ventricles. Okay, so the reason being, as I told you, 3 to 4 times they are replaced. Okay, it means that the secreted CSF they are reabsorbed back, and a new one is always secreted. Okay, so about I don't know. I think they're having network problem. Here, there is nothing because no request has come. I think there is some problem from their side. I mean, network problem might be there. Okay, let them try again. So automatically they will be admitted. Okay. So about 2/3 or more of CSF originates as secretion from the choroid plexuses in the 4 ventricles, mainly in the 2 lateral ventricles. So as you know, from the epithelium of the choroid plexus, okay, 2/3 of them, they will be, 2/3 of the CSF produced is from the epithelium of the choroid plexus. Additional small amount of fluids are secreted by ependymal surfaces of all the ventricles. So as I told you, these are around 2/3, okay, are secreted, and small amount will be secreted from the ependymal cells also. Then I've already shown you the ependymal cells. Okay, so the main one will come from these epithelial cells of the choroid plexus, and they are also known as I told you, modified ependymal cells. Okay, and small amount may also be secreted from the arachnoidal membranes. Okay, small amount comes from the brain itself to the perivascular spaces. Okay, so these are small volume of areas from where small volume of CSF is secreted. Okay, so the main one will be from the epithelial cells of the choroid plexus. Okay, secretion of CSF. Okay, I've already shown you the villi. Okay, so this is the structure of the villi of the choroid plexus again. Okay, the capillaries in the choroid plexus are fenestrated. That means they're having some pores. Okay, let's say this is the, you see this is the blood vessel or capillary. Okay, this is the blood vessel or this is the capillaries. As you can see from here, fenestrations are there. Okay, that means pores are there in between the cells. So because of that, the constituents of plasma, they can easily escape into the interstitial fluid. Okay, so fenestrations are there in the capillaries. Hence, provide little resistance to the movement of small molecules, ions, and water. Okay, so because of this penetration, okay, movement of molecules, okay, it is very easy. That means little resistance is there to the movements of small molecules, ions, and water. Okay. A barrier is formed, however, by the junctional complexes between the epithelial cells. But if you see the epithelial cells of the choroid plexus here, I told you that tight junction is formed in between the cells. Okay, it is very tight blood CSF barrier. So this is known as blood CSF barrier. I've already told you. Okay, so although here constituents of plasma, they escape into this interstitial fluid, but movement from this area into the lumen of the ventricles to become CSF, it is not easy. Okay, because of the tightness of this junction. Okay, or we can say because of this barrier. So this barrier restricts the passage of molecules and ions into the CSF. Okay, here many of them they escape into the interstitial fluid, but their secretion into the lumen of the ventricles to be CSF, it is difficult. Okay, restriction is there because of tight junction. Okay, so the choroid plexus epithelial cells therefore form what is known as blood CSF barrier. I already told you. Okay, now let's see how secretion is then take place, because secretion should take place. Although there is, what to say, this one is there, barrier is there. Okay, let's see the first point. Secretion of fluid into the ventricles by choroid plexus depends mainly on active transport of sodium through the epithelial cells lining the outside of the plexus. Okay, now we see, let's say this is the villi. Okay, this is the villi of the choroid plexus. You know, these are epithelial cells of the choroid plexus, and there is a tight junction. Okay, here this enlarged portion, it is shown here. Okay, in this diagram. Okay, here sodium transport, active transport of sodium is important. So this is the CSF. Okay, so this is the interstitial fluid, and here we know that next to this interstitial fluid there will be the blood vessel. Okay, so you see this sodium transport is important. Sodium, they are secreted. So when sodium is secreted, you already know that this will be followed by the chloride ions. Okay, in renal tubules also we have discussed. Chloride ions will follow because sodium it is positive, it will pull chloride ions also. Okay, and you know that here also there is one carrier protein which transports sodium, potassium, and two chloride ions into this lumen of the ventricles to become components of the CSF. Okay, so the two of these together, that means sodium and chloride, okay, increases the quantity of osmotically active sodium chloride in the cerebrospinal fluid, which then causes almost immediate osmosis of water through the membrane, thus providing the fluid of the secretion. So it is very clear that when you see sodium chloride as well as potassium in this example, when they are secreted, okay, you know that now the quantity of the solute is now increased in the CSF. So this will be followed by water, by osmosis, aquaporin 1, through aquaporin 1. So you know very well that whenever solute is secreted or reabsorbed also, it will be followed by water. Okay, so that the water volume here in the CSF will also be increased in this space. Okay. In the choroid plexus, activity of sodium potassium pump is closely associated with the secretion of CSF. So it is clear already. Less important transport processes move small amount of glucose and bicarbonate ions into the CSF and potassium out of the CSF into the capillaries. So at the same time, sometimes potassium it is reabsorbed back into the capillaries. Okay, and at the same time, glucose and bicarbonate also they are secreted here to become the consequence of the CSF. Therefore, the resulting characteristic of the cerebrospinal fluid become the following. Number one, osmotic pressure approximately equal to that of plasma. So the osmotic pressure of this CSF, okay, osmotically active substance concentration, it is approximately similar to that of plasma. Number two, sodium ion concentration also approximately equal to that of plasma. So here, just like the extracellular fluid, okay, in the plasma, the concentration of sodium will also be similar. Okay, chloride ions about 15% greater than in plasma. So, but thus chloride ion concentration, it is higher than that of the plasma. Potassium ion approximately 40% less. Okay, potassium ion, it is lesser as compared to that of plasma by around 40%. Okay, glucose also, it is around 30% less. That I don't know. I told you that it is. I don't know. I have to admit them because it is all okay automated. Okay. Sometimes I think it used to hang. Okay, just tell whenever there is a problem. Okay, it used to hang. I think sometimes. Okay. So these are the difference between we can say composition of CSF and the composition of the plasma. Okay. Now CSF is it is secreted into the lumen of the ventricles. Okay, ventricles of the brain. How they are flowing through the central nervous system. Okay, route of CSF. Okay. So here you know that these are the two lateral ventricles. Okay, here you can see lateral ventricles. Okay, this one and this one. Okay, these are two lateral ventricles, and the wall of the ventricles, as you know, they are covered with this choroid plexus. And choroid plexus, epithelial cells, they secrete CSF into the lumen of these lateral ventricles. Okay, now CSF is secreted into the lateral lumen of the lateral ventricles. And then this fluid now, it will move through foramen of Monro. Okay, so this area is the foramen of Monro. Okay, and then it will move to the third ventricle. Okay, so the third ventricle. So this is the third ventricle. Okay, this is the lumen of the third ventricle, and then the CSF. Then it will move through the ducts of aqueduct of Sylvius. Okay, so this is the aqueduct of Sylvius, and then it will move to the fourth ventricle. Okay, so this area is the fourth ventricle. This is the enlarged portion again. This is the ventricle again. Okay, from the fourth ventricle, this will can move through this foramina of Magenti and Laska. Okay, so here you can see, or this too. Okay, it will move through this one, or here also it can move. Okay, and then what will happen is that it will go to subarachnoid space of the brain and the spinal cord. Let's say this is the spinal cord. Okay? So the fluid, it may move like this. Okay, the direction here, it will be like this, or it will come back. Okay, and then you can see they will be in the subarachnoid space also here. Okay, here they are moving in the subarachnoid space also, from this one also through the subarachnoid space. And you know that now reabsorption will take place, okay, through the subarachnoid membrane into the venous sinus. That is why, as I told you, 3 to 4 times CSF is replaced, because reabsorption is it. When there is reabsorption, okay, there will be secretion again. So it is continuously, CSF is continuously replaced. Okay, that is why 500 ml is secreted, but that is 3 to 4 times more than that of the actual CSF present inside the what to say, spaces of the central nervous system. Okay, so these are the root. Okay, now functions of the CSF. Buoyancy, we all know very well this one. The brain exists in neural buoyancy in the CSF. Or we can simply say that the brain is floating in the CSF. Okay, the brain is floating in the CSF. Okay, this allows the brain to maintain its density without being impaired by its own weight, which will cut off blood supply and kill neurons in the lower section without CSF. So we all know that whenever there is a gravity, okay, so weight will be increased. Suppose brain is here, okay, brain is there, and it is covered by the skull. Okay. So because of gravity, okay, it will pull towards the ground. Okay. But as you know that since the fluid is there, this brain it will float in the CSF. Okay, that will reduce the weight of the brain. Here we can see example. For instance, the actual mass of human brain is about 1400 to 1500 grams, or 1.4 to 1.5 kg. Okay. However, the net weight of the brain suspended in the CSF is equivalent to a mass of only 25 to 50 grams. So we all know that when you do the swimming or when you are inside the pool and all, okay, you all know that your weight has decreased. That is why you can float in the water also. Just like that, there is also a reduction of the weight of the brain when it is, you can say, immersed in the CSF. Okay, so that will reduce the weight. Otherwise, if there is no CSF, means the weight of the brain will be too much and it will crush, or we can see that because of gravity. Okay, there will be, it will cut off the what to say, blood supply and all. Okay, everything will be disturbed. Now the second function of CSF, protection. CSF protects the brain tissues from injury when jolted or hit by providing a fluid buffer that acts as a shock absorber from some forms of physical injury. Still, no one is there, no request. I think it's hanging again, no? Okay. So we know very well this one also protection. Okay, shock absorber, you know that. So CSF acts as a shock absorber when there is injury or when jolted or hit, okay, on the head. Okay. The third one is prevention of brain ischemia. So prevention of brain ischemia is aided by decreasing the amount of CSF in the limited space inside the skull. This decreases total intracranial pressure and facilitate blood perfusion. So CSF is increasing the blood supply to the brain. Okay, blood perfusion is what we say, facilitated by the CSF. Okay, otherwise there can be ischemia. Ischemia means decreased supply of the blood to the particular tissue or organ. Okay, homeostasis. CSF allows for regulation of the distribution of substances between cells of the brain and neuroendocrine factors, through which slight changes can cause problems or damage to the nervous system. It means that CSF, it is a fluid, so it is important for distribution of some important substances from one place to another in the CSF. Okay. Otherwise, if there is slight change in all this concentration of these substances or neuroendocrine factors, okay, it can cause problems or damage to the nervous system. Okay, for example, high glycemic concentration disrupt temperature and blood control, pressure control, and high CSF pH causes dizziness and syncope. Okay, so the concentration, okay, normal concentration of the CSF, it is very important. Okay, concentration of substances. Okay, number 5, clearing waste. CSF allows for the removal of waste products from the brain and is critical in the brain's lymphatic system. So as you know, it is a fluid. Okay, it is also important for the removal of substances. Okay, it will drain into the subarachnoid space. You know that the venous system. It will drain into the venous system. So that waste material will be removed. Okay. So this is the composition of the composition of plasma and the CSF. Okay. So most of the composition it is similar, but the protein content there is a big difference. Okay. So in the plasma, protein which is expressed in milligram per 100 ml, it is 7,000, but in the CSF it is only around 20. Okay. So this is a big difference. And here another lactide also there is a big differences there, but not that big. And this one also, this one and this one also. Okay. So that is the CSF. Number 2, another extracellular fluid, synovial fluid, or it can be said that simply synovial. Okay. So what is synovial fluid? it is a viscous fluid. Viscous fluid, that means viscosity is quite high found in the cavities of the synovial joints or in the joints. Okay. So this is found. This fluid is found there in the joints. The principal role of synovial fluid is to reduce friction between the articular cartilage of synovial joints during movement. So you know that this fluid is important in reducing the friction. Okay. Otherwise, there will be wear and tear. Okay. Okay. If drying of the joint is there or no synovial fluid is there. Okay. Ultimately, cartilage injury will be there. Okay. Synovial fluid is a small component of the transcellular fluid. So you know that they are also a part of the extracellular fluid. Okay. So the inner membrane of synovial joints is called the synovial membrane. Here you can see the synovial membrane. Okay, here this one and this side also. Okay, so this is the synovial membrane. Here also the synovial membrane is there. Okay, synovial membrane secretes synovial fluid into the joint cavity. Okay, so in this joint cavity, synovial fluid is secreted by the synovial membrane. Okay, so synovial fluid is an ultrafiltrate from the plasma. Okay, we can say that most of the components of the synovia, it is directly filtered from the plasma. Okay, synovial fluid contains proteins derived from the blood plasma and proteins that are produced by the cells within the joint tissue. So here you can see some proteins, they are derived directly from the plasma, drained directly from the plasma. But some proteins, they are produced by the cells within the joint tissues that we will see. Okay. So what are the important components of synovial fluid? Number one, hyaluronan, okay, secreted by the fibroblast-like cells in the synovial membrane. So here you see this synovial membrane, they are secreting this hyaluronan, okay, which is not coming from the plasma directly, but synthesized by the cells of the synovial membrane. And lubricin is also there, they are secreted by the surface chondrocytes of articular cartilage. So you can see these are the cartilage, okay, cartilage membrane, and these cells, they are secreting the lubricin. So this side is also, this is also the membrane of the cartilage, okay. And interstitial fluid, which are filtered directly from the plasma. Now this space, the space, okay, will be filled with all these constituents, okay. This fluid forms a thin layer, which is roughly 50 micrometer at the surface of the cartilage. It also seeps into microcavities and irregularities in the articular surface, filling all empty space. Whenever there is crevices or spaces, this fluid will be filled with, this space will be filled with the synovial fluid. The fluid in articular cartilage effectively serves as a synovial reserve. Okay, so in those cavities, synovial fluid are there. Okay, so they are, we can say, reserve synovial fluid. Okay, during movement, the synovial fluid held in the cartilage is squeezed out mechanically to maintain a layer of fluid on the cartilage surface. Okay, when you do movement, okay, the fluid in the cartilage, okay, they are squeezing out. Okay, reduce the friction between the two cartilage. Okay, it will come out. The fluid will be seeping out or squeezed out. Okay, which is known as breathing lubrication. Okay, so functions of synovial fluid. Number one, you know very well that it is for reduction of the friction. Synovial fluid lubricates the articular joints. Number two is shock absorption. Okay, so just like the CSF, they are also shock absorption. You see, this is a dilatant fluid possesses rheopeptic properties. Rheopeptic properties means becoming more viscous under applied pressures. Okay, the synovial fluid in diarthrotic joints becomes thick the moment shear is applied in order to protect the joints. Okay, so whenever you apply the pressure, okay, the synovial fluid will increase in its viscosity. Okay, so this is important for that lubrication. Okay, subsequently it thins to normal viscosity instantaneously to resume its lubricating function between shocks again. Okay, then after that it will become viscosity will reduce again. Okay, another important function of synovia is nutrient and waste transportation. They supply oxygen and nutrients. On the other hand, removes carbon dioxide and metabolic waste from the chondrocytes. That means the cells of the cartilage in the surrounding cartilage. And number 4, molecular sieving. Okay, pressure within the joint forces hydrogen in the fluid against the synovial membrane. This form a barrier against cells migrating into or fluid migrating out of the joint space. So they are acting as a barrier also. Okay, for the movement of some cells from one place to another. Okay, composition of the synovia. Okay, composition of the synovial fluid changes during an individual lifetime due to changes in mechanical loading and deep joints, degradative diseases. So these are the main components, okay, of the synovial fluid. Okay, now the last topic for excretory system we'll discuss. Okay, that is kidney function in birds. So birds, they are having different structure of the kidney, okay, which is quite different from that of the mammals. Okay, so in urine formation and elimination, birds have many similarities to mammals, but major differences are notable. Okay, what are the similarities with that of the mammals? Number 1, glomerular filtration. Okay, so plasma is filtered from the glomerulus into the Bowman's capsule. Okay, just like mammals. And there is also tubular reabsorption in the birds, and also tubular secretion. Okay, and the urethral urine can have an osmolarity that is above or below that of the plasma. That you know very well. Okay, because the glomerular filtrate. Okay, the filtrate, it changes its osmolarity or osmolarity when it is passing through the renal tube. Okay, so this is also happening in case of the birds. Okay, and the osmolarity, it may be below plasma or above that of plasma. So what are the differences from mammals? Number 1, there are two major nephron types. Okay, so this is different. It is not like superficial or juxtamedullary nephrons. Okay, we'll discuss afterwards. Presence of renal portal system is there. Okay, as separate, or we can say renal portal system is there in birds. And there is also formation of uric acid instead of urea as the major end product of nitrogen metabolism. Okay, so then product of nitrogen metabolism is uric acid instead of urea. It is urea in case of mammals. Number 4, post-renal modification of urethral urine. So after, in case of mammals, when urine is formed, when it is passing through pass out of the kidney, there is no modification. As it is, it will be excreted. But in case of birds, after it leaves the kidney, okay, the urine is still modified, okay, before excretion. And number 5, the last one is absence of urinary bladder. So there is no urinary bladder in case of birds. Okay. Now let us see the structure of the kidney in case of birds. Okay. Just like mammals, it is also a paired organ, but you see that each kidney, it is divided into 3 lobes. Okay, number 1, cranial. Let's say this is the cranial one, and this is the medial, and this is the caudal. So this is the right kidney, and this is the left kidney. Okay, 1, 2, 3. Okay, 3 lobes are there in each kidney: cranial, medial, and the caudal. Now you see, each lobe is composed of lobules again. Okay, so this diagram, let us see. Diagram number 1. Okay, in this point number 1, this is the kidney. 3 lobes are there. This is the cranial, medial, let's say this is the caudal. Okay. So, and you see here, this area, this small area, when it is, this small area, when it is enlarged, it is a lobule. Okay, so that means each lobe of the kidney is consisting of a numbers of, again, thousands of, we can say, lobules. Okay, so this is the structure of lobule. Okay, so a lobule somewhat resembles a mushroom. Okay, so here it is. So this is the head portion of the mushroom. Okay, or this is the stem. Okay, so cortex cortex corresponding to the cap of the mushroom. Okay, so this is the cortical region. Okay, the cap or the head. Okay, this area is the cortex, and the stem corresponding to the medulla. So this is the medulla. So this is the cortex. Okay, so lobule is looking like a mushroom. The cap or the head is the cortex. Okay, cortical portion, and the stem is the medullary region. So ureter transport urine from the kidneys to the cloaca. So as you know, there is no urinary bladder. So ureters, here you can see from here, it starts from here. Okay, let's say this is the opening of the ureters. Okay, so this is the ureters. Okay, here you can see this is the ureter. This is the right ureter going directly to the cloaca, and this is the left ureter. Okay, then also directly going to the cloaca. Okay, so this structure, it is the, what to say, reproductive organs. Okay, tubules. This will also be discussed in reproduction. Okay, so these are ductus, vas deferens or ductus deferens, whatever. Okay, so cloaca is the common collection site for digestive, reproductive, and urinary organs. So this is quite different if you compare with the mammals. Okay, cloaca is a common site, common collection site for digestive, that means fecal material, or reproductive means whether it is the ovum or the semen, and urinary organs means it is also a collection site for the urine. Okay, so this cloaca, okay, it will collect reproductive, secretion, and even the fecal water as well as the urine. Okay, so this is not happening in case of mammals. Okay, now I told you that there are two types of nephrons in the birds. Okay, and you know that there are approximately 2 legs of nephrons in the cicape. Okay, so you just imagine 2 legs of nephrons in the cicape. Avian kidneys are characterized by having 2 major nephron types. As I told you, number 1 is the reptilian nephrons. Okay, here you see reptilian nephrons. Okay, this is the reptilian nephrons. Here, this dark color, this is the, what to say, the glomerulus. Okay, and then here it will start the, what to say, proximal convoluted tubule. Okay, PCT, and it will join directly the collecting duct. Okay, there is absence of the lumen that we'll see afterwards. Okay, so this is the reptilian nephrons. Another one is the mammalian nephron. Okay, here the mammalian nephron. Okay, so mammalian nephron, as you can see, this is the glomerulus, and you see the loop of Venn is very long, which is going to the inner side of the medulla and going back and join the collecting tubule again. Here another mammalian nephron going down, going down and coming back and join the collecting duct. Okay, that you will see afterwards. Okay, so there are 2 types of nephron, reptilian and mammalian. Okay, let's see first the structure of reptilian type nephron. Okay, reptilian type nephrons are located in the cortex and lacks loop of Henle. So there is no loop of Henle. Okay, so this is the structure. Here you see glomerulus. It is there. It will filter plasma, and it will go to the proximal convoluted tubule instead of loop of Henle intermediate. This tubule is there, and then this cell tubule, and then collecting duct. Okay, now since there is lack of loop of Henle, less reabsorption of water. Therefore, reptilian type nephrons are not capable of concentrating urine. Okay, it is like the superficial nephron. Okay, they are also located in the cortex. Okay, they are not able to concentrate the urine. Okay, now let you see carefully. Okay, the second diagram. I will point with this pointer. Okay, so this one is the reptilian nephron. Here also a reptilian nephron. Here also a reptilian nephron. And below here, this is reptilian nephron. This is reptilian nephron. This is also reptilian nephron. So we have here in this diagram 6. Okay, 1, 2, 3, 4, 5, 6. 6 reptilian nephron are there. Okay, let's see from this diagram. It is very clear. Okay, So this dark dot-like structure, can you see or not? This dark spot, is it visible or not? Can you see?
Yes, sir.
Okay, so this is nothing but this dark spot. Okay, terminal pointed structure. It is nothing but the glomerulus. Okay, this is the glomerulus. Is it clear or not? Okay, and this, as you can see, this is this red color. Okay, this blood vessel, it is arterial blood supply. From arterial blood supply, it will. So here we have the afferent arterial. Here, then afferent arterial. Here we have the glomerulus, and from the glomerulus, you see, it will become efferent arterial. Here, so this is the efferent arterial, and then it will join the, what to say, peritubular capillaries. So this whole structure is peritubular capillaries. I repeat again, this is the afferent arterial entering the glomerulus, and after coming out of the glomerulus, it becomes efferent arterial. Then efferent arterial, it will join the peritubular capillaries. Okay, so same thing will be there in all other reptilian nephron. Here also the same thing will be there. Okay, and you know that in the reptilian nephron. Okay, so now this is the loop of proximal convoluted tubule. Okay, and you know that intermediate tubule is there, and it becomes distal convoluted tubule. And distal convoluted tubule, then it will drain to the collecting duct directly here. So this collecting duct, this dark color, black color, can you see or not? Okay, so this is the collecting duct. So collecting duct is common for all the nephrons. Okay, it is not like that in mammals. Okay, here you see the collecting duct. It is coming, it is passing like this. Okay, can you see the pointer? Okay, so the collecting duct is moving like this. Okay, and it is common for all the nephrons, whether it is reptilian or mammalian nephrons. Okay, so this distal convoluted tubule here, it will drain into the collecting duct. Here also distal convoluted tubule, it will drain here. Okay, here also distal convoluted tubule, it will drain into the collecting duct. Here also same thing. Here also the same thing. Okay, is it clear or not? From the structure. Okay, so intermediate segment I already told. Okay, what about the mammalian type of nephron? Okay, so they are located near the medullary cone. That means near the medullary cone means this area. Okay, most of them, they are in the, we can say, the medullary cone. But the glomerulus and all, they are in the proximal convoluted tubule, they are in the cortical region. Okay, and extend their loops of Henle into the cone. So in case of mammalian nephron, loop of Henle is present. Okay, and it is very long also. It has a well-defined loop of Henle that are grouped into a medullary cone, the part of the lobule that correspond to the stem of a mushroom. Other structures in the medullary cone are the medullary collecting duct and vasa recta, all of which enter at the weather cortical end of the cone. So from the diagram, it will be clear. Okay, now here we see there are, in this diagram, there are only two mammalian type of nephron. Can you see the pointer? Can you see the pointer? Stylus pointer, can you see or not? Oh, okay. This dot-like structure, okay, this is the glomerulus again. Glomerulus of the mammalian type of nephron, okay? And then from the glomerulus, proximal convoluted tubule, you see, you just trace the pointer. It is, the loop of Henle is very long, okay? So it is going to the deeper side of the medullary area. And then it will come back, okay? Pointer not visible. Visible. Okay, this dark color, can you see black color? You can see now. Okay, this small black color. Okay, or not? This is the glomerulus. Okay, glomerulus,
Yes, sir.
Okay,
Yes, sir.
now it will start the loop of Henle. Proximal convoluted tubule. Can you see this one? or
Yes,
not?
sir.
Okay, so now it is going down towards the medullary region and it becomes loop of Henle. And this loop of Henle is very long. Okay, so it is going to the deeper part of medullary cord. And what will happen is that after that, it will come back. Okay,
No
this
visible, sir.
visible or not? Okay.
Yes, sir.
So it is going back, and what it will do is that it will drain this, then it will drain into the, after becoming distal convoluted tubule again, it will drain into the common collecting duct. Can you see? This is collecting duct. Okay, I already told you. Okay, so it will drain into the collecting duct. Clear or not? I'll trace. Can you see the pointer? Small pointer. Red in color. Okay, so I'll trace. This is the glomerulus. Okay, and then it becomes proximal convoluted tubule. Then it becomes loop of Henle. Okay, can you see? Can you see or not? Oh, going down, and then it will loop back. It will ascend towards the cortex again. Okay, so after reaching the cortex, this DCT, it becomes now distal convoluted tubule. DCT, then it will drain into the collecting duct. So this collecting duct, as I told you, it is common for all the nephrons. Okay, so here you see, this is the collecting duct. Okay, which will drain urine into the, what to say here, ureteral branch. Okay, clear or not? So what about the second mammalian type of nephron here in this example? Okay, here this is the glomerulus. Okay, and then become proximal convoluted tubule, looping down towards the medulla and coming back again, and this again it becomes distal convoluted tubule, and distal convoluted tubule will drain into the collecting duct again. Okay, clear? So whether it is mammalian type or reptilian type, all nephron drain into the common collecting duct. Okay, here this is the common collecting duct, this black in color. Okay, the function of this collecting duct is that to drain urine towards the cloaca. Okay, is it clear or not?
Yes, sir.
Yes, sir.
Okay. So from the diagram itself, I think you can trace. Okay, it's very simple. Okay. So now the tubular fluid from both types of nephrons are received by common collecting ducts. I already told you. Okay, this common collecting duct here, this black color tubular structure, it is the collecting duct. Okay, so collecting ducts also extend into the medullary cord where it exposed to the interstitial fluid concentrating gradients similar to those of mammalian kidney. So this point is important. Okay, so you see the collecting duct, they are exposed to the medullary tissue. Okay, this collecting duct, they are exposed to the medullary tissue. You know that in case of mammals, the medullary interstitium, it is having high osmolarity. Okay, high osmolarity is maintained here in this area for concentration of the urine. Okay, just like the mammalian kidney. Here in case of avian kidney also, this interstitial fluid of the medullary region, they are also having high osmolarity. And these collecting tubules, as well as the loop of Henle, they are exposed to that area, that high osmolarity, which is important for the concentration of the urine. Okay, all urine from a lobule leaves the common ureteral branch. Okay, so it will through the common collecting tubule, collecting duct. Okay, urine will drain into this ureteral branch. Avian kidney can alternate between the use of reptilian type and mammalian type nephrons depending on the need for water conservation. Okay, just like the mammals. Okay, it can alternate whether reptilian type or mammalian type should be used. Okay, for example, when birds are given a salt walk, okay, a majority, that means, and thus the need to conserve water for diluting the added salt, a majority, about 80% of the reptilian type nephrons shut down to zero filtration. That means reptilian type, they will not function under this one. Okay, when a bird is consuming large amount of salt. Okay, Also, the whole kidney GFR is reduced to about 40% of the control value. Of that amount, an equal amount of urate comes from the nephrons of the reptilian type and of the mammalian type. Okay, all these things you can read it by yourself. Okay, I'll not repeat. Okay, so it is just like the mammalian kidney. Okay, when there is increased intake of the salt, okay, there will be, what to say, that reptilian type, they will not function. But another type of that one, nephron will be doing its main work. Okay, that means to concentrate urine. The mammalian type nephron will do the concentration of the urine. Now next is the renal portal system. So this is important and it is simple also. Okay, so avian kidney has renal portal system for a portion of blood supply to perfuse the tubule. So there is extra blood supply for the kidney in case of birds, which is known as renal portal system. Venous blood arising by this means comes from the hind limbs. All these things are the anatomical structure. Okay, let's forget about that one. The renal portal blood enters the kidney from its periphery, supplying afferent blood to peritubular capillaries. So you just remember this one. Okay. Oh, can you see what I have just underlined and circled? Okay. So this is the renal portal vein here. Here another renal portal vein is there. Yes, sorry. Okay. So this is causing extra blood supply. Okay. So you see that now. Okay. Now let us trace this renal portal vein. Okay. Can you see the pointer? Okay. So this light blue in color. Okay. This is the renal portal vein. Okay. Now it is passing like this in the lobule of the kidney. Okay, here you see that here it will cause. Okay, it will supply. It will be, what to say, it will supply blood to the afferent arterial. Here you can see this is the afferent arterial. Okay, and here in this example also this is the afferent arterial. Okay, here also it become afferent. It will supply afferent arterial. Here also same thing will be here. Okay. So this is another renal portal vein. Okay, it is supplying the afferent arterial, or we can say all the whole peritubular capillaries. So all these are peritubular capillaries, the venous side and the arterial side are there. Okay. Within the peritubular capillaries, it is mixed with efferent arterial blood coming from the glomeruli. Okay. Now this is what to say here in this example. This efferent arterial. Okay. Then it will be mixed here and then drain into the central vein. Okay. So the mixture perfuses the tubules and proceed to the central vein. So this is the central vein. Okay. So this big vein all will drain into the central vein. I will not repeat. It is estimated that the renal portal system supplies 1/2 to 2/3 of the blood to the kidney. Okay. So what about the concentration of the urine? So as I told you, mammalian type of nephrons, they are important for concentration of the urine in case of birds. Okay, in birds, so all these things I think you can read it by yourself. Okay, there is no need of explaining it. It is similar to that of mammals only. Okay, there are some statistical difference only. Okay, so there is counter-current mechanism also that we have already discussed. Okay, now here also similar condition is there, but I want to explain here. A corticomedullary osmotic gradient exists in the peritubular fluid and medullary cone. Okay, see the first diagram. Okay, let's say this above this area, it is the medullary region. Okay, and this is the cortical region and this is medullary region. So the medullary region is having, just like the mammalian kidney, they are having higher osmolarity here. Okay, hyperosmolarity is here. Okay, here also we can say this area is having hyperosmolarity. So here interstitial fluid osmolarity will be higher. Okay. The osmotic gradient is established by the loop of Henle of the mammalian types of nephrons. Here, loop of Henle, you see, I've already shown you. Here, long loop of Henle again, counter-current mechanism, just like in case of mammals, is also taking place in case of birds. Okay. This is maintained by vasa recta. All these things we have discussed. All tubular fluid, whether from the fronts of the reptilian or the mammalian type is exposed to the osmotic gradient. Okay, now all tubular fluid, they are exposed to the osmotic gradient. Why? Because they are drained, all are drained into the collecting ducts. Okay, so all the fluid from the all types of nephrons, okay, they are drained into the collecting duct. And you know that from this diagram, collecting duct is passing through the medullary cord, which is having high osmolarity here. Okay, this is because of the I'll not repeat. The renal response to the antidiuretic hormone of the birds, which is known as arginine vasopressin, like that in mammals, consists of an increased permeability of the collecting duct. So the name of ADH in case of birds is arginine vasopressin. It was arginine vasopressin in case of the birds. Okay, here it is vasopressin. Okay, so again here there will be increased permeability when there is presence of high amount of arginine vasopressin. Okay, the tubular fluid reaches osmotic equilibrium with the interstitial fluid surrounding the tubules, thus becoming hyperosmotic plasma as collecting ducts pass through the medullary cone. So you already know that when the fluid is passing through, this collecting duct is passing through this one. If reabsorption of water will take place, large amount of reabsorption will be large amount of water reabsorption will take place in presence of arginine vasopressin, just like the presence of ADH in case of mammals. Okay, so urea 1 to 10% of the total urinary nitrogen plays virtually no role in establishing hypertonicity. Okay, so this is a difference again. In case of birds, the presence of urea in the interstitial fluid of the medullary region is very important to generate that hypertonicity. Okay, but in case of birds, urea is not important. Okay, hypertonicity is most likely created by sodium chloride. So sodium chloride is important in causing hyperosmolarity of the medulla of the birds, in case of birds. Okay, the maximum concentration that urine can attain is caused through the concentration of interstitial fluid at the tip of the medullary cone. So this is also thus similar to that of the mammals. Okay, and in birds with free access to water, urine osmolarity is nearly isosmotic to the plasma. So here you can see that the mechanism, it is similar with that of the plasma, but the actual value is different. So in case of mammals, it was around 1200 milliosmol per liter or per kg. Okay, but in case of birds, it is lower. It is 320 milliosmol per kg of water. During dehydration, osmotic concentration increases to 2 to 3 times that of the plasma. So it can increase. Okay, under normal condition, the normal one is this one, but under dehydration, it can increase. Now, uric acid formation and excretion. The metabolism of proteins and amino acid results in the production of nitrogenous end products. Okay, so we all know that metabolism of proteins and amino acid results in nitrogenous end products, and you know that the most common ones are ammonia, urea, and uric acid. Okay, so in case of, so this will account for 2/3 or more of the total nitrogen excreted. Accordingly, animals are divided into 3 groups. Okay, depending on whether their main nitrogenous excretory product is either ammonia, urea, or uric acid. So animals are divided into 3 groups depending upon the measured nitrogenous end products excreted. Okay, ammonia group, urea group, and uric acid group. Okay, so I'll not do here. Okay, let me read it. This one. Ammonia is very toxic substance and must be either rapidly excreted or converted to less toxic substance such as urea and uric acid. Okay, so ammonia has to be converted into urea or uric acid to be excreted since it is toxic. Okay. Among vertebrates, the ammonia excreting group is confined to animals that are entirely aquatic. Okay, fishes and all. Okay, the ammonia, a relatively diffusible substance, is quickly discharged into the vast reservoir about them. That means they are fishes. They are living in sea. Okay, whenever they are releasing this ammonia, it will go directly to the water, and it is a vast area. So the concentration of ammonia cannot go high, so it will not be toxic for them. Okay, urea excreting group is found in mammals and amphibians. Okay, so these are not repeat. So what about now? Our interest is that birds. Okay, birds, the third group of the animals. Okay, they are the birds and dry living reptiles. Okay, their main nitrogenous, their main protein and product or nitrogenous substances excreted is in the form of uric acid. Okay, since the embryo must develop, so this is interesting. Since the embryo must develop in a limited supply of water in the egg. Okay, we all know that birds, they are laying eggs, and the fetus, it develops inside the egg only, not inside the uterus. Okay, it is better that the excretory products are deposited as insoluble materials that do not require water for their removal. Okay, so if the excretory products are in the form of solid, okay, so water requirement for removal of waste product it is reduced. Okay, so that is why birds, they remove this in the form of uric acid. It would be necessary to eliminate liquid urine form if urea were the end product. Okay, so if the end product is urea, okay, water is necessary for removal of the waste products. Okay, but in case of bird, this is not the case since it is developing inside the egg. Okay, uric acid in birds is formed in the liver from ammonia, so all these things are there. It is also believed that the kidney may be set for. So the interesting thing is that uric acid is freely filtered at the glomerulus and is also secreted by the tubules. So tubular secretion is the dominant process. Okay, so although they are freely filtered, okay, but most of the uric acid excreted is coming from the tubular secretion. So when greater amounts of uric acid in the tubule exceed its solubility, okay, its solubility means too much of uric acid is secreted, so we all know precipitation will occur. Okay, uric acid continues through the tubules in the precipitated form and appears in the urine and stool. It is coagulum. Okay, uric acid as such, the color is white. Because uric acid is no longer in solution, it does not contribute to the effective osmotic pressure of the tubular fluid, and obligatory water loss is avoided. Now it is in the solid form, so it is not contributing to the osmotic pressure of the tubular fluid. Okay. So birds have considerable control. This is excretion of electrolytes. Okay. Control over the tubular reabsorption of sodium and chloride. Okay, I think this you can read. These are all similar to that of mammals. Okay, angiotensin, how important it is for the reabsorption of sodium, but for the secretion of potassium we have already. Aldosterone also the same thing. Okay, so NP also we have discussed all these things. And you also know that renin, angiotensin, aldosterone system, which involve angiotensin, aldosterone, okay, renin, okay, those things we have already discussed. Okay. So where there is salt and volume, the blood angiotensin to stimulate reduction in GFR. So all these things you already know. Okay. So when there is salt and volume loading, that means when there is increased salt concentration or salt ingestion or volume loading is there, increased blood volume is there. The response to angiotensin B2 becomes natriuretic and diuretic. That means removal of excess water or removal of excess sodium. Okay, in mammals, angiotensin to stimulates only anti-natriuresis, anti-diuresis. Okay, but not natriuretic or diuretic. Okay, so this is the difference. Okay, aldosterone is presumed to have an action on the kidney similar to that in mammals, wherein it is associated with sodium reabsorption component. So same thing is there. All this thing. Aldosterone is likely the principal regulator of plasma potassium concentration. This one also similar to that of mammals we have discussed. Then bird secretes NP from the atria of the heart. NP has natriuretic and diuretic activity, much similar to its function in mammals. Again, same thing. That means it can increase sodium excretion as well as water excretion. What about calcium? Under normal condition, the kidney reabsorb more than 98% of the calcium. Okay, Anything? So actually, all these are similar to that of this one, but mammals. That is why I'm going fast. Okay. So there are some slight differences. Okay, regarding how much percentage is reabsorbed. Okay. So you already know that the importance of parathyroid in controlling calcium concentration. Also, this one also we have discussed. About 60% of the tubular load of phosphate is excreted in the urine. Okay, this is normal rule. Parathyroid hormones inhibit phosphate reabsorption and stimulate its secretion. This one also the same thing. So the dual action of the hormone, that means PTH, on the reabsorption and excretion of calcium and phosphate, assists in the maintenance of appropriate calcium and phosphorus ratio. So PTH or parathyroid hormone, it is always important in controlling the concentration of calcium and phosphate in the plasma. Okay. Now the important point here, the last topic. Okay, modification of urethral urine. So as I told you, in case of mammals, after leaving the kidney, okay, the urine is not modified. It's simply drained into the urinary bladder and excreted. But in case of birds, there is a difference. Okay. Modification of urethral urine. Okay, post-renal modification of urethral urine is possible because of its exposure to the membranes of cloaca. Okay, so it is also exposed to the membranes of colon and ceca because of retrograde flow caused by reverse peristalsis. That means, let's say this is the kidney. Okay, the kidney, it is producing the urine, and through the ureters it is entering what is known as, this is the cloaca. Cloaca is divided into coprodium, urodium, and proctodium. Okay, three parts are there. This is 1, 2, 3. Okay, so urine is entering the urodium. Okay, but this urine, before it is excreted here through the opening of the cloaca, retrograde flow will be that. That means it will flow back towards the first coprodium, and then it can go to the colon also. Okay, so modification of the urine will take place here. Okay, so the cloaca function mainly as a storage organ, and as you can see here, it is divided into coprodium, the most anterior part, urodium, the medial one, and the proctodium, the caudal part. Okay. Now, what is the function of the coprodium? Coprodium collects fecal matter from the colon. It is said that this is a digestive tract, so it will collect the fecal matter. What about the urodium? It is the area that collects urine directly from the ureters. Here you can see, this is the ureter. Okay, here from the, this is not the urinary bladder. Actually, this diagram is wrong. Okay, there is no urinary bladder. So you can see here, so it will be here. Okay, urine will be collected there. The reproductive tract also connects with the urodium. Okay, here it is not showing. You know that, even the reproductive tract, okay, it will drain into the urodium. The urodium and coprodium then empty into the proctodium before being excreted outside of the body. Okay, it is in the proctodium the urine and fecal matter mix. Okay, here mixing of the urine and the fecal matter will be there. But before that, as I told you, retrograde flow of the urine is there. Here, changes will take place. Okay, changes will take place. That means the composition of the urine will change. Okay, it can go up to even up to the ceca as well as the colon. Okay, so the major post-renal modification of urethral urine takes place in the colon. Okay, here in the colon it is major changes in the urine take place here. Water reabsorbed from the colon follows the active reabsorption of sodium. So here you know that sodium chloride is reabsorbed. Okay, from the colon, this urine. Okay, and then this will be followed by water by osmosis. That you already know. Sodium chloride and water reabsorption does not occur from the ceca and could involve urine water. Does occur from the ceca and could involve urine water if retrograde flow progress to that location. Even if the urine flow, retrograde flow urine is progressing up to this cecum, here also modification can take place. It means sodium chloride and water reabsorption further can take place here. Okay. Urine characteristic and flow. Blood urine unmixed with feces is cream color. When it is not mixed with feces, it is cream color and contains thick mucus. And precipitated uric acid is mixed with the mucus. Okay, it will mix with the mucus. Secretion of mucus probably facilitates transport of the precipitated solute, similar to the role of mucus in equine urine. Okay, so it is clear that after modification, okay, this urine, it will come along with the fecal matter, and here proper mixing will take place in the proctodeum. Okay, and then after that it will be excreted along with the fecal matter. Okay, what is avian salt gland? Okay, one or two slides are here. All birds have glands in the head known as the nasal glands. Okay, so this is the salt gland. In many species, produce a non-serous, non-mucoidal secretion having an uncertain function. In species with a marine habitat, these glands are well developed and are capable of producing copious secretion containing high concentration of sodium chloride. Okay, so when there is secretion of this salt gland, okay, the concentration of sodium chloride used to be very high. Okay, because of their osmoregulatory function in this species, they have been called salt glands. Okay, you see, these glands secrete the excess salt when food with a high salt content is ingested or when seawater is drunk. Okay, so this salt gland, it is important in secreting excess salt which is present inside the body. So we all know that excess salt in the body, it is harmful for the body. So when that is happening, okay, this salt gland will excrete those excess salt. Okay, then there will be reduction of the sodium chloride in the body. Okay, the salt secretion flows through the salt ducts into the nasal cavity, runs through the nerves. Okay, drips off from the tip of the beak. The salt gland secrete only sodium chloride and none of the other substances excreted by the kidney. Okay, so it is said that only sodium chloride is secreted along with water. They function only when there is salt load, otherwise they are at rest. Okay, so this salt gland, as you can see, it is very important for reduction of the salt concentration in the body. Sometimes this is important because kidney may not be sufficiently excreted excess salt. Okay, then this salt gland will also help. So this is present in some species. Okay, so this is for today. Thank you.
Thank you.
Thank you, sir.
Okay.